So welcome to another conference at the 243rd meeting of the American Astronomical Society. It's Wednesday, January 10th at 2:15, Orleans. I'm Ben Cassese, the AAS Media Fellow for this year. I'm joined by Susanna Kohler, the AAS Press Officer, and Carrie Hensley, the Deputy AAS Press Officer. Today's session is titled Stars, and Exoplanets. Press releases will be distributed following this meeting and eventually added to the press kit. And press releases from this morning's meeting have already been distributed. So just to once again, the format of these sessions, I will introduce our speakers and they will go down the line one by one to their presentations. We ask that you hold your questions and applause until the very end while we do one joint session and thank everyone, all of them. If you're joining us online, we ask that you add your questions to the Zoom chat where Carrie can help read them out. And Susanna will be passing around a microphone in the room as well, so everyone can hear that on Zoom. So as I said, all of these talks today are stars, disks, and exoplanets. So up first, we'll have Brandon Schweers of Lehigh University with a presentation titled Paternity Tests, Matching High-Latitude B stars to Open Clusters of Their Birth. Following will be Travis Metcalfe of the White Dwarf Research Corporation, speaking about wind-breaking exoplanet host star 51 Pegasi. Next will be Christopher Stark of NASA Goddard, talking about JWST's new view of the Beta Pictoris suggests recent episodic dust production from eccentric inclined secondary debris disk. Might be the longest title we have of the week, but an interesting one. Next will be Stephen Giacalone of Caltech, talking about how do massive planets form, gaining new insight by measuring the orbital tilt of a rare transiting brown dwarf. And finally, we'll have Alyssa Jankowski and Melinda Soares-Furtado, an Earth-sized addition to the 400 million planetary system in the Ursa Major Moving Group. All right, so I'll hand it over to our first presenter. It is not working, so I will not hand it over yet.
Good too. Apologies. Oh, there you go.
Thank goodness they didn't have Zoom back then, otherwise never would have worked.
Oh, he moved something?
Yeah, you can.
Hey, oh, he did this. Let's
I think he was trying to make it better.
Let's try to put that back in.
It's promising.
Okay. Now let's
See if it propagates, but feel good about this. All right, so I'm going to get us into screen sharing mode here. And we're going to cross our fingers.
Thank you, Ben, for that lovely introduction. Hello, everyone. I hope you're having a wonderful Wednesday afternoon. As you just heard, my name is Brandon Schweers, and I'm an undergraduate at Lehigh University. Today, I'm going to be talking to you about stellar paternity tests, the name of a project I've been working on with Dr. Ginny McSwain at Lehigh University for the past year. Now, I know you may be wondering, Brandon, what is a stellar paternity test? To which I say, Excellent question. Anyway, first we have an introduction. So as you all are well aware, star formation primarily occurs in the thin disk in open clusters. Once you leave the thin disk, you'll mostly find older population 2 stars. However, there is a small number of young B-type stars that we've observed at these high galactic latitudes, and this is very unusual. We wouldn't expect these stars to be outside the thin disk where we think they were born. So our theory is that these stars were born in open clusters in the thin disk, but were ejected either due to dynamical interactions between the open cluster members or from a supernova ejection. But either way, it's our objective to identify the parent clusters for each of these orphan stars. And because these stars are so far away from home, so far away from their parents, they are almost kind of like the astronomy equivalent of finding a lost kid in a mall. And so we begin by using a Python package called Galpy and Gaia DR3 data to calculate the trajectories of nearly 100 B-type stars that we've selected for this study and 1,400 known open clusters in the Milky Way galaxy. Here you can see a short little animation of the trajectories of our 95 B-type stars over the past 30 million years using was calculated using the Galpy Python package. It's an edge-on view of the galaxy. So on the x-axis, you have galactocentric R, how far away these objects are from the center of the galaxy. And on the y-axis, we have galactocentric height, how far away they are from the galactic plane. And you can really see some of these stars are very far away from the galactic plane, even up to 9 or 10 kiloparsecs, which is well outside the thin disk. And so by calculating the trajectories for all 1,500 objects, we search for times of past intersection between pairs of an orphan star and a parent cluster. Here's one such pair that proved a positive match. In blue, we have the open cluster Berkeley 89. And in red, we have the high-latitude orphan star HIP 111563. That's a bit of a mouthful, so I'm going to refer to this pair as pair 1. On the left, we have a top-down view of the galaxy, of these objects as they orbit around the galaxy. And on the right, we have another edge-on view to emphasize just how far away this star is from the galactic plane. Here we have another pair that flagged as a positive match in the same format as before, this time with open cluster Loudon 372 and high-latitude star EC 054 or 05490. And again, this one I will call pair 2 because that's a mouthful. And using this method, we identified 22 orphan stars that matched at least one open cluster. And some of them matched up to 13 clusters. But obviously, one orphan cannot have 13 parents. So we refined our results using a color magnitude test. In this color magnitude test, any pair that flagged as a positive match in the trajectory test, we plotted an HR diagram. And what we looked for was any high latitude star that falls in line with the grouping of the as its proposed siblings. So on the left, we have the HR diagram for pair 1, and on the right, we have the HR diagram for pair 2. Pair 1 proved to be a poor DNA overlap. The high latitude star is far away from the grouping of the rest of the cluster members, and you can see that this cluster is probably a much older cluster, much older population. Any B star that was in the cluster when it formed had already died out. So that star is not from this cluster. But on the right, we do have a we do have a very good overlap in DNA between the star and its siblings. The high latitude star falls in line with the overall main sequence pattern of the cluster. And so we can say that the star formed around the same time as the cluster members of Loudon 372. And so it's further evidence to point towards this star could have come from this cluster. Using this method for all of our potential matches, we reduced our list down to 15 orphan stars that matched at least one open cluster, and some still matched to multiple. So to reduce that multiplicity, we turn to a cluster density analysis. This is because the denser a cluster is, the more gravitational interactions will be happening between the cluster members. And so a denser cluster will be more likely to eject a star. So in the cases where a orphan star matches with more than one parent cluster in both the trajectory test
break your flow. Added the. It was frozen. Sorry.
The videos.
We had the video back. Or no? Okay. Note that the rest of the meeting is not hybrid. It's only this where we're trying to do both.
Okay, so bottom line here is that stronger fields and less complex fields, simpler fields, shed more angular momentum and slow the rotation more effectively. Okay. Okay, so what did we know before about the relationship between magnetic field properties and stellar evolution? So to understand the history and future of our own sun, we need to study other sun-like stars that are both younger and older. So those are shown here as yellow points, with the sun here as a white marker. And so we're looking at a measure of the relative magnetic field strength on the vertical axis as a function of the age of a sun-like star. So what we already knew from previous studies was that the magnetic field strength actually drops very, very quickly in the first half of the lifetime of the star like the sun. So you can see here from its birth to its present age, the magnetic field strength dropped by 400% for the sun. But in the second half of its life, the sun is expected to change its magnetic field strength only by 40%. So a much more stable environment in the second half of its lifetime. So that's what we knew already before. So what's new? Our new observations, we used the Large Binocular Telescope in Arizona. It's the largest optical telescope in the world with a collecting area about 12 meters. It's two 8.4 meter mirrors. We used the LBT to construct a magnetic map of the surface of 51 Peg, which is a middle-aged sun-like star. So here I'm showing three different views of this map, where the blue and the red regions represent areas with opposite magnetic polarity, like the north and south poles of the Earth. Okay? So the map allows us to reconstruct the magnetic field lines of the star, showing complex regions that appear as these closed loops, okay? And simpler regions where the stellar wind can escape, shown as the sort of open lines in the background. Okay. So the magnetic field of a sun-like star is not only growing weaker, but also more complex over time, which has two effects. It throttles the stellar wind because it only escapes on those simpler magnetic field lines, and it reduces the strength of magnetic braking. So we've made similar measurements of the strength of magnetic braking for a variety of sun-like stars, as well as hotter and cooler stars at different ages over the last few years. And we'd previously found that although younger stars follow our expectations, so here I'm showing on the vertical axis the relative strength of magnetic braking as a function of the normalized rotation period. So it's a measure of rotation with slow rotation on the right-hand side. So what we found is that although these younger stars follow our expectation of standard models that follow the relationship between magnetic field properties and rotation, at some critical value of the rotation, stars suddenly drop their magnetic braking by a factor of 10. Okay. Some of these earlier measurements have relatively large uncertainties, but 51 Peg makes it unambiguous that this effect takes place before you reach the rotation rate of the sun. And so this In other words, basically weakened magnetic braking, this phenomenon of weakened magnetic braking has already started in our own solar system. Okay, so it might just be a coincidence, but on the only inhabited planet that we currently know about, which is the Earth, this transition to weakened magnetic braking occurred around the same time that life emerged from the oceans onto land. Now, life underwater was well shielded from the harmful particles and radiation produced by the young sun, but it wasn't until the magnetic environment became more stable that life ventured onto the surface. So our results suggest that the best places to search for technological civilizations like humanity that might exhibit some techno-signatures may be around stars that are middle-aged and older after this transition has already taken place. Thanks.
Do we still have a video connection? Great.
Hi there, everyone. Thanks. I'm Chris Stark. I'm from NASA Goddard, and I am Deputy Observatory Project Scientist for the James Webb Space Telescope. I understand that I set the record for the longest title at this session, so I'm providing an alternative title here, which is JWST's Unexpected New View of the Beta Pictoris Debris Disk. This is based on work that's been peer-reviewed and accepted for publication and should appear on arXiv tonight or tomorrow. A bit of background, Beta Pictoris is a nearby star that hosts a very rich planetary system. The star is close, it's bright, and the planetary system is so conspicuous that it's been imaged since the 80s. We know that Beta Pictoris has at least 2 exoplanets, and it's one of very few systems that is known to harbor extrasolar comets. The most conspicuous feature of this planetary system is a very bright edge-on debris disk. A debris disk is all of the dust and larger planetesimals that collide to grind down and produce what we see. It is so nearly perfectly edge-on that we can use the vertical structure of this disk to learn about the underlying planetary system. And in the image on the left, Sally Heap published in 2000 this disk data and showed that interior to 100 AU, the disk appears warped. So it's not just a nice flat disk. The image on the right, published in 2006 by David Golomowski, suggests that maybe that disk is not warped, maybe it's actually a distinct secondary disk. And this has been discussed in the literature, and I will touch on it in this talk. One of the most interesting things about this putative secondary disk is that it harbors a lot of carbon monoxide. And so you can see the carbon monoxide line emission in this ALMA data shown from Bill Dent's 2014 paper. Not only is there a lot of carbon monoxide, but it's very asymmetric and very clumpy. Now, it's surprising that we see carbon monoxide at all because it has a photodissociation time of just 150 years. So it should be broken apart, and we really shouldn't see much of it. So this led Dent to suggest that either a recent massive collision occurred, causing all of that clumpy carbon monoxide, which they deemed as unlikely, or there's continuous asymmetric production of carbon monoxide. And I'll touch on this in my talk. So we set out to observe the Beta Pictoris debris disk using JWST's NIRCam and in this image here. So on the left side of this image, we see a fork. This is due to an extension of the secondary disk to hundreds of AU. Surprisingly, that extension disk. Instead, what we see is this very obvious curved feature coming off of the disk that we've dubbed the cat's tail. And in the top half of the image, we see all sorts of sort of striated, tendrillous nebulosity. The cat's tail and the nebulosity have never been detected before and are unlike anything we've seen in any other debris disk to date. So this was very puzzling. What really surprised us is what we saw when we made a false color image combining the 15 micron and the 23 micron data. So that's what I'm showing you here. It's immediately obvious that the secondary disk, which appears bluer in this image, is very asymmetric. It is truncated on the right half of this image, but it extends to hundreds of AU on the left side. So this disk is very eccentric. The main disk, which appears mostly red in this image, is very symmetric. You can also see that the cat's tail and this nebulosity are blue, like the secondary disk, meaning that they are dynamically linked somehow to that secondary disk. Now, the reason that it appears blue in this image is because that dust is hotter. So apparently, the secondary disk is made of a different material than the main disk, and that material is hotter. We put a lot of effort into trying to understand what materials could be heated up to this temperature, and the only material that seemed to explain it was very porous, or in other words, fluffy, organic refractory material. This material would look very black to us. It'd also be a poor radiator in the infrared, and it might be similar to the type of material that's being returned from the OSIRIS-REx mission. They're finding very dark, carbon-rich material. So this is the first major result of our work, that we have indeed confirmed that there are two distinct disk components, one of which is hotter than the other and likely composed of a different material and likely organic refractory material. The second result that I'll cover is what we learned when we attempted to explain what this cat's tail is. It looks almost as if material is being pulled off of the midplane of the disk. This is very difficult to do dynamically. And what we think we are seeing is an optical illusion of sorts. So what we settled on for our best fit model is shown here. The right panel shows our best fit model of the secondary disk face on, so not from the orientation that we actually observe at. You can see that there is this eccentric disk component here that explains the majority of that secondary disk. But if you model individual collisions happening in the system, you can end up with very large extended tails of debris associated with that. It's not unlike the physics behind a comet. And that tail can be pushed out to thousands of AU very quickly. And if you then orient a system or a model like this to the orientation that we observe, on the left, you can see it appears as though it is coming off of the midplane of the disk. So here's a quick animation showing that collisional event happening and evolving in time. A stream of material would emanate from the collision while it orbits the star, extend to 1,000 AU, and if we then orient this to the observed orientation, you can see we get something that looks similar to the cat's tail. Now, my favorite part of this model is that we had to invoke two things. To explain the shape and flux of the cat's tail, we again had to invoke porous organic refractory material. So we now have two independent lines of investigation leading us to the same material. And second is that the time scale of this collisional event is 150 years, the same time scale as the photodissociation for carbon monoxide. So we think this event may explain not only the cat's tail, but also the clumpy carbon monoxide that was observed. So what this means in general is that debris disks, but specifically beta Pic, may be more active than we previously thought. We think we might be seeing signs of a very recent collision, and this may explain prior detections of carbon and carbon monoxide gas. What it means for JWST is that JWST may be providing an unexpected new window into debris disk dynamics and composition. The MIRI instrument should be very sensitive to this type of material, and we should go looking for it around additional debris disks. And finally, again, this material may be similar to what has been returned from the OSIRIS-REx mission. Thank you.
Hello, everyone. My name is Stephen Giacalone. I'm a NSF postdoctoral fellow at Caltech, and today I'll be telling you a little bit about my research looking into the formation of ultramassive planets. So we know, based on the solar system, that planet formation is a variety of outcomes. We have objects as small and as low mass as asteroids, to rocky planets like Earth, ice giants like Neptune, and these really massive gas giants like Jupiter. But there's quite a big gap in mass between a Jupiter-like object and a low-mass star. So the lowest mass stars have masses that are about 80 times the mass of Jupiter. And so we can ask the question of, why don't we have planets somewhere in between these two in the solar system? And it turns out that these do exist out there in the galaxy. We have detected them. I'm sort of interchangeably going to refer to them as ultramassive planets and brown dwarfs here. But the bottom line is that they're very rare, and so they're poorly understood because we don't have a lot of them to study. So one of the big questions revolving around these objects is, how do they form? Do they form more like planets, or do they form more like binary stars? In the planet formation framework, you have clouds of gas in the interstellar medium that collapse. It forms a star and a circumstellar disk, sort of like the disk you saw in the last talk. And from this disk, you form a planet. Eventually, the disk disappears, and you're left with a star-planet system, like the solar system. In the binary star formation framework, you instead have multiple clouds of gas that contract, collapse, and form stars simultaneously. And you get binary stars. So theory predicts that these ultramassive planets and brown dwarfs should be able to form via both of these pathways. But most of the evidence so far is that they're forming like stars. And we know that from the chemical compositions of these objects and from the orbits of these objects. There's really not a lot of evidence yet that they can form similar to planets at the midplanes of these disks. And so in this talk, I'm going to present some new key evidence that these brown dwarfs can in fact form like planets in the midplanes of disks. So one of the best ways we have to probe the formations and dynamical evolutions of these objects is by studying their orbital tilts relative to the spin axes of the star. So here I have a star in the middle, surrounded by a disk. The dotted line in the star is its equator, and the star is rotating in the direction indicated by these arrows. So again, eventually the disk disappears and you're left with a planet. In the planet formation view, because the disk we expect to mostly be aligned with the spin of the star, you would have an orbit that is aligned with the spin axis of the star. So everything is in this nice line. And this is pretty much how the solar system is, so within a few degrees. In the binary star framework, you really don't expect to have a preference towards alignment in these angles. So you might instead have a star that is spinning in the same direction as I showed before, but your planet or brown dwarf could be at a big angle like this, almost 45 degrees. We've even found things at 90-degree angles. And so no preference towards alignment for the binary star formation case. So to combat this sort of uncertainty, we went and determined the orbital tilts of the brown dwarf GPX-1b. So GPX-1b is a transiting brown dwarf, meaning it passes in front of the star along our line of sight. It's about 20 times more massive than Jupiter, and it orbits pretty close to a central star. Its orbital period is only a few days. It was discovered in 2021 by the Galactic Plane Exoplanet Survey and the NASA TESS mission. And our data suggests that the orbital tilt of this brown dwarf is very small. And so the orbit of the brown dwarf is very much aligned with the spin axis of the star, which again suggests that this brown dwarf may have formed in a disk like a planet rather than outside of a disk like a star. And I apologize for not being able to show our actual data. The paper is still in prep, but hopefully soon that will be submitted for publication. So how do we actually do this measurement? I think this is one of the most interesting parts. So this measurement takes advantage of the fact as something transits, it's blocking out different Doppler shifted parts of the star. So you can see on the star here, the left is blue shifted and the right is red shifted, and that's because of the rotation. And so as your planet or your brown dwarf transits, you get these little variations in the stellar spectrum as a function of time, as is shown on the right here, these little wiggles. And if you have a very precise high resolution spectrograph, you can actually trace out how this wiggle behaves over time. And the behavior of the wiggle over time essentially tells you what the angle between the orbit and the spin of the star is. So we got our measurements using the Keck Planet Finder spectrograph, which is a new, extremely stable high resolution spectrograph at the WM Keck Observatory, which is extremely capable of detecting these things. It was just commissioned last year. And so we're expecting to get a lot more cool measurements like this in the future using this instrument. Okay, so to quick recap, we don't know yet if these ultramassive planets and brown dwarfs can form like both planets and like stars. So that would be within disks or outside of disks. To gain new insight, we measured the orbital tilt of the brown dwarf GPX-1b, and our results suggest that it likely formed in a disk like a planet due to the alignment of its orbit. We plan to observe similar systems. We only have one measurement like this so far, and so we want to get a lot more of them to do robust statistical analyses of these types of systems. And we'll be doing that with KPF, which is really important for this because, like I said, these objects are rare, which means they're mostly found around faint stars, which means we need a really big telescope and a really precise spectrograph to do these kinds of measurements. So KPF on Keck is going to be one of the best tools available for doing this. And that's all I have. Thank you.
Hi, my name is Alyssa Jankowski. I'm up here today with Dr. Melinda Soares-Furtado, my mentor. And I just want to note that this presentation is based on work that is currently accepted by the Astrophysical Journal for publication and will be available on the archive after this presentation. And I'm here today to introduce a young Earth-sized planet orbiting a sun-like star. Now, first things first, I want to emphasize the importance of young planets. Young planets represent a critical point in planetary evolution, going from the earliest stages of a planet first being formed all the way to a mature planetary system that is stable. Now, there are a couple issues with this, however. First things first is that planetary systems don't spend a lot of time at this age range, which is roughly younger than 500 million years old. Planets spend most of their time as mature systems. So they're hard. We have to catch them at that specific point in time. And even if we do catch them, we might not know, as planetary systems are very difficult to age date. So we only know of a handful of planets that are confirmed to be young exoplanets. Now, one of the processes that happens to young exoplanets is atmospheric loss. Any planet that is larger than Mars will accumulate a large hydrogen-helium atmosphere. Now, most planets don't retain that atmosphere. It gets lost over time. For example, Earth had twice the atmosphere that it does today. So how do we go from this, a planet with a gaseous atmosphere, to this, a planet with a more rocky planet with a thin atmosphere? Now, one solution to finding out how we get there is through moving groups, and this is how we find our ages. Moving groups are a collection of stars that all formed from a common molecular cloud or nebula. And these member stars have common chemical compositions and velocities in space, and these give us our age constraints for their constituent stars. Specifically today, I'm going to be talking about the Ursa Major moving group. It is the nearest moving group to Earth. It is very young and rich in bright stars, including many Big Dipper stars. So if you're out of New Orleans, you can take a look at the Big Dipper and know that some of those stars are part of this moving group. And this group is actively being searched for more young exoplanets. One such system in this moving group is the HD 63433 system. Now, the star of this system is very, very similar to the sun with one caveat. It is 10 times younger. The sun is about 4.2 billion years old, where this system is about 400 million years old. Now, a previous paper had discovered two other planets in this system, planet B and C, and they're about Neptune-sized, or sub-Neptune sized, sorry. And these were discovered using the transit method. Now, for those of you who aren't aware, a transit is when a planet passes in front of its star from our perspective, causing the star's brightness to dim. And one of the main ways that one of the main instruments we use to discover these transiting exoplanets is TESS, the Transiting Exoplanet Survey Satellite. Now, TESS scanned the sky in what's called sectors, and in its primary mission, it's got sectors of the whole sky, which enabled us to find many, many transiting exoplanets. Now, at the time that MAN 2020 was published, they had access to one sector of TESS data for this system. Now we have more data of this system as TESS has reobserved the system. And that has allowed us to find this, a third dip in the transit now, or a third transit in discovered for this system. Now, everything on the left side of this plot is our new data, and everything on the right side is our old data. So you can see that really shallow transit was just lost in the noise from TESS. And with more data, we were able to finally pick that out, giving us HD 63433d. Now, this planet is just about the size of the Earth. And I know what you're thinking. You're thinking we have a sun-like star and an Earth-sized planet. Is this thing habitable? Unfortunately, no. This planet has an orbital period of about 4 days, which, for context, if we are comparing this to our solar system, all 3 planets in this system fit comfortably within the orbit of Mercury. So very, very close to their host star. And when you are this close to your host star, a couple things happen. One, you are likely tidally locked to your star, meaning that one side is always facing your star. The other thing is that things get very, very hot. So the day side temperature is about 1500 Kelvin, which is hot enough to melt gold. So unfortunately, no habitability here. However, there are still a lot of important things that can be gained from this system. First things first is we want to reobserve this system using Hubble and JWST to get more of an insight on any atmosphere that might be being lost from this system. The other thing that we want to do is we want to apply the constraints that we currently have from this planet to get a better idea of evolution of Earth-sized planets as a whole. Now, just to summarize, we are presenting the nearest Earth-sized planet younger than 500 million years old, orbiting the sun-like star HD 63433. It is about 400 million years old, with a length of its year being about 4 days, 5 hours. It is most likely tidally locked to its star with a temperature of 1500 Kelvin, which gives it a lava hemisphere. And further characterization of this planet's atmosphere is critical for understanding planetary evolution. Thank you very much.
Okay, thank you all to our speakers. So let's begin Q&A. Do we have questions in the room?
I'm Govert Chilling, freelance from the Netherlands. With a question for Chris. I know the pitfalls of small number statistics, but do you have any idea how often these kind of collisions can occur in the beta PIC disk or in other disks?
Yeah, that's a great question. So we estimated that the minimum mass of the debris that we observe roughly is equivalent to a 100-kilometer diameter body, which is on the order of a large asteroid in the solar system. It might be 10 or 100 times larger. Estimating the true mass of the progenitor is wildly unknown. So the other thing that's wildly unknown is estimating the probability of these events. To really do that, you have to know what the orbital distribution and number distribution of the parent bodies is, and we have no idea. But there are some methods we can use to take a wild guess at it. And if we take that minimum mass of a 100-kilometer body, we estimate that within the last, we estimate a 65% chance of that occurring within the last 150 years. A 65% chance of the minimum mass object required to produce this within the last 150 years. So in terms of, large asteroids colliding in Beta Pictoris, it should happen very frequently.
Leslie Sage from Nature. I have two questions, one for Brandon, one for Travis. So Brandon, in your traceback, did you account for star-star interactions as the runaway stars were heading out, or did you assume those would be negligible?
I assume those would be negligible and did not account for those.
Okay. And Travis, so putting aside the life stuff, if you are you arguing that the presence of planets introduces the complexity in the stellar magnetic field? And if so, could you use the presence of slow rotation as another indicator of the presence of unseen planets?
No, the presence or absence of planets doesn't play into the evolution of the magnetic field properties in this case at all. There may be some extreme cases where there are interactions, but in this case and in all the cases we've studied, this is purely a feature of how sun-like stars evolve over time.
Hi, this is Ethan Siegel from Start to the Bang, and I'm going to continue harassing this one side of the table. I have two questions, one for Chris and one for Brandon. Chris, you talked about abundant carbon and carbon dioxide or monoxide in this debris disk, and I'm curious why that part requires an explanation. Aren't these extremely common features to detect in debris disks? We just normally only detect them in absorption rather than emission. And isn't the reason we expect this is in emission is because the beta pic system is directly edge on? I thought that was the conventional explanation. Are you saying this is something different?
Well, the reason that we would detect them in absorption is because it's edge on. We detect them in emission around a number of disks. Some of those other disks that we have, it's a handful, some of those other disks that we have detected carbon monoxide around also show potential signs of collisions. The presence of carbon-rich gas in Beta Pictoris has always been something that has been debated. People have suggested that the bodies in the system themselves are carbon rich. That's not necessarily the case. It could be that you have a body that is, differentiated, and the material that is from the collision, the material that was given off is, from a different layer that is primarily carbon rich. So we don't know necessarily whether the material that is producing the carbon monoxide itself is carbon rich, or there's some sort of, selection type effect going on.
And my second question for Brandon. Brandon, I apologize. I know you're an undergrad, so I apologize for this question in advance, but I have to ask it. The average time scale for a star to come within 1 light year of the sun is a few 100,000 years, 200,000 or 300,000 years on average. You're talking about tracing back individual stars that travel through the Milky Way for 30 million years and assuming that their trajectories that they're on now can be simplistically traced back without any perturbations to them. And that would be a good tool for identifying them and their host clusters and where they came from. My question is, why do you think the current trajectories of any of these stars can be traced back with high precision for 30 million years?
Yes, thank you for the harassment. So originally we actually traced them back for 50 million years. And we realized going back so far, the further you go back, the more error there's going to be in the calculation. So we limited it to 30 million years. We think 30 million years is a good stopping point because even though there could be perturbations in the trajectories that could bump the stars into a different trajectory, including a second test with the color magnitude is a good way to ensure that such a match could be possible. So we have two pieces of evidence to point towards the star coming from this cluster instead of just one. And so by having two pieces of evidence, it further strengthens our case.
Josh Lovell from the CFA. Sorry, Chris, it's another question for you. You make a very compelling case for this cat's tail feature in the disk. But that suggests there's going to be some dynamical evolution. I wondered over what timescales you might expect that feature to change, and is this something that we can follow up over the next decade?
That's a great question. The answer is yes, we should be able to follow this up. So, I agree, this is a hypothesis at this point as to explain that tail. And there are a number of ways that we can go about testing that. One idea is we expect the tail to affect the dust that composes the tail to be size sorted with the smallest grains at the tip. So we could look spectroscopically whether we see signs of that size distribution over the length of the tail. We could follow up with ALMA to see if we can resolve the orbit of the progenitor potentially. The most exciting thing is that this tail moves so quickly that we expect it to move 1 to 2 pixels in JWST's Miri imager within 3 years. So we could go back now, re-image it, and determine whether we're right or not.
Hi, Sarah Smith, Texas State University. I'm sorry, this is going to be another question for that half. But Travis, I was wondering, this may be for one out of the scope of the talk and also not in your specific field, but I'm curious as to whether there's been any thought of, because you see that the magnetic field is not entirely following that standard model and has that critical point, if whether that could be due to the fuel sources within the star having some kind of a change, and if it is, whether or not you might be able to model it based off of like some kind of initial condition of what is happening within the star at its core.
That's a great question. So we don't currently have a predictive model that would shows this transition at middle age for stars like the sun, but we do have some qualitative ideas about what could give rise to it as a natural feature of a stellar dynamo that builds a magnetic field in the limit of sufficiently slow rotation. And so it just seems to be a natural feature of things that we already understand reasonably well.
Governor Schilling again, freelance, with a follow-up question for Chris. This talk about the time scale for this cat's tail. I was wondering, what is the expected lifetime for the structure? How long do you expect to be able to see it? And if those kind of collisions happen every couple centuries, might we be able to see remaining structures from previous collisions?
Yeah. We think we might be. So all of that nebulosity that was in the image can to some degree also be explained by other recent collisions. And if you look at that image, there were some features right next to the cat's tail that probably could be also on the order of 150 years old, but would have been smaller collisional events. But we also see some different types of structures in that nebulosity that could be explained by collisions from a different location in that secondary disk, and they would be on the order of
1,000 years old. So what we're suggesting is not that we're seeing just one collision, but that we're seeing episodic collisions occurring in this disk that may explain many of the features that we observed.
Hi, I'm Harmony from the University of North Alabama. This is my penguin. And this question is actually for Alyssa. And I'm sorry if this is a little bit of a basic question. I'm currently an undergrad student, so I'm not deep into astrophysics and astronomy just yet. But could you please explain the significance of young Earth-like planets and studying them, please?
Well, I'm an undergrad too, so don't worry about that. Yeah, so young Earth-sized planets present pathways to really truly understanding how Earth-sized planets form and evolve in general, which we're on an Earth-sized planet, so that could present some very helpful existential pathways for how our own planet evolved and getting a better idea of that, and then being able to get a better idea of how we find systems that might have Earth-like planets as well. So that's one of the major reasons why this size of planet is so exciting.
Corey Powell reporting for IEEE Spectrum. This is another question for Alyssa about the planet. You identified two really interesting sort of geophysical aspects of the planet: the possibility of very high atmospheric loss, and that you might have a lava hemisphere. What kind of data would you need to collect to verify those two things? Is that within the reach of what JWST can do, for instance?
Yeah, sure. So we are currently working on a JWST proposal, and that is definitely within the reach of JWST. What we would be looking for currently is spectroscopic lines from elements other than hydrogen or helium that would indicate atmospheric loss. So Planet C, I didn't get to talk about this, but Planet C had been discovered in a different paper, Zhang et al. 2022. Planet C had been discovered to be currently outgassing a hydrogen atmosphere, but not Planet B. So we wouldn't expect hydrogen or helium outgassing from this new Planet D. So that's more what we're looking for, heavier elements being outgassed from this planet's atmosphere. And that is well within the reach of JWST observations, yeah.
Hi, my name is Maya and I'm with Purdue University. So I have two questions for Stephen. The first is, you mentioned that you measured the orbital tilt for GPX-1b and came to the inference that it forms like planets. So my first question on that is, for future work, are there other features you might consider looking into to distinguish between the possibility of it forming like a planet versus star, for instance, the kinematics or the magnetic field strength?
Yeah, so magnetic field strength is something that we're looking into in our data right now. So people sometimes use magnetic field strength for these really short period planets. Specifically, they can probe the H-alpha line, which is one of the hydrogen transitions. And that line gets stronger sometimes when something is transiting. And you can essentially map the strength of that line to the strength of the magnetic field in your hot Jupiter or your brown dwarf. So that's something that we're looking at right now. We don't really have definite results. As far as other things, the atmospheric composition is a really promising avenue. So directly imaged brown dwarfs that are at like 100 to 200 AU tend to have compositions that closely match the sun, like their stars. But we haven't really done atmospheric studies for these short period aligned brown dwarfs yet. And so it'd be interesting to see if these aligned short period brown dwarfs have more planet-like compositions instead of more star-like compositions. And so that's something that you can do with JWST. I'm not aware of any programs that are doing it right now, but something interesting in the future potentially.
I see. Thank you for that. And my second question, follow up from that, what was the cutoff or range of cutoff values, if any, between what you consider to be low orbital tilts versus high orbital tilts?
Yeah, so that is a little bit more fluid. The high orbital tilt systems tend to be at angles greater than about 30 degrees. And then for reference, the solar system is, I think everything's within like 7 or 8 degrees. So in our system, specifically GPX1, it was about 7 degrees. And so we consider that to be within the confines of aligned. But yeah, the question of, how aligned is something that I think people could have a conversation about.
Thank you.
Okay, we are just about out of time. So I'd like to thank all of you for your questions. Let's thank our speakers one more time. And I'd also like to quickly thank the sponsors for this session, the USRA, and let you know that we will be back here in this room tomorrow at 10:15 for a press conference titled The High Energy Universe. So hope to see you then.